Welcome back to Electrical and Electronic Principles for Neurodiagnostic Professionals. This is lesson number 3. In our last lesson, we introduced Ohm's law and learned the relationship between voltage, current, and resistance. In this lesson, we'll put Ohm's law into practice. We'll begin by solving a few example problems and then apply the same principles to circuits containing resistors connected in series, in parallel, and in a simple combination circuit. By the end of this lesson, you should be comfortable calculating total resistance, current, and voltage in these basic circuits. These are fundamental skills that you'll use repeatedly throughout the remainder of this series and throughout your career in neurodiagnostics. So let's get started. In the last lesson, we introduced Ohm's law. If you remember, Ohm's law states that voltage in volts equals current in amps times resistance in ohms. Now let's solve some equations using Ohm's law. Here is a simple circuit. It consists of a voltage source, in this case a battery connected with 2 wires to a resistor. If you remember, this is the electrical symbol for a battery. This is the electrical symbol for a resistor. In this circuit, current flows out of the battery through the resistor and back to the battery. Let's start using Ohm's law with a simple problem. Here we have a 10-volt battery and a 500 ohm resistor. Question: what is the current in milliamps in the circuit? Let's use Ohm's law. V equals I times R. In this problem, V equals 10 volts. R equals 500 ohms. We will set the current to I. We can rearrange the equation to I equals V divided by R. So plugging in what we know, I equals 10 volts divided by 500 ohms. Therefore, I equals 0.02 amps. Using the 4-step process we discussed in Lesson 1 to convert from amps to milliamps, we move the decimal place 3 spaces to the right and we get 20 milliamps. The answer is 20 milliamps. Let's try another one. Let's say we are doing an SSEP. We measure the resistance of our stimulation electrodes and we find that they are 5 kilo ohms. We set our stimulator to 30 milliamps. What voltage is our machine putting out to deliver the 30 milliamps across our 5 kilo ohm electrodes? Again, V equals I times R. We know I equals 30 milliamps. We know R equals 5 kilo ohms. We will represent voltage with a V. Let's fill in our equation. Voltage equals V, I equals 30 milliamps, and R equals 5 kilo ohms. But in order to use the formula, we have to convert 30 milliamps to amps and 5 kilo ohms to ohms. Using our 4-step prefix conversion process, we convert 30 milliamps to amps by moving the decimal point 3 places to the left. So 30 milliamps equals 0.03 amps. Similarly, to convert 5 kilo ohms to ohms, we move the decimal point 3 places to the right. 5 kilo ohms equals 5,000 ohms. To solve for V, we multiply 0.03 amps and 5,000 ohms. V equals 150 volts. So in order to deliver a 30 milliamp stimulus into our 5 kilo ohm electrodes, our machine is outputting 150 volts. Let's do one last problem before we move on. We are doing SSEPs in the OR. We are stimulating at 50 milliamps. Our machine is showing that it is delivering 40 volts. What is the resistance of our stimulating electrodes? Before we solve this last problem together, I'd like you to try it on your own. Pause the video, work through the problem, and see if you can find the answer. Once you've solved it, write your answer in the comment section below before continuing the video. When you're ready, press play, and we'll solve it together step by step. Welcome back. Did you solve the problem? Let's go through the solution step by step. V equals I times R. We can rearrange the equation to R equals V divided by I. In this case, we will represent resistance with an R, we will set V to 40 volts, and I to 50 milliamps. Again, in order to use the equation, we need to do some conversions. In order to convert 50 milliamps to amps, we move the decimal point 3 places to the left. 50 milliamps equals 0.05 amps. V equals 40 volts, so it's in the proper units for the equation. Plugging into the equation, R equals 40 volts divided by 0.05 amps. R equals 800 ohms. The resistance of our stimulating electrodes is 800 ohms. Try this next time you are doing a case to see if your stimulating electrodes are below 5 kilo ohms. Let's move on. Up to this point, we've been working with simple circuits, a battery connected to a single resistor, but real electrical circuits aren't always that simple. What happens when we have multiple resistors? How does Ohm's law apply in those circuits? Let's look at the two basic ways resistors can be connected. Here we have two resistors connected end to end. These resistors are said to be in series. Current flows in a single path from the battery through the first resistor, then through the second resistor, and finally back to the battery. As we'll see, the current is the same everywhere in a series circuit. The voltage, however, is divided across the resistors. The voltage across R1 will usually be different from the voltage across R2, but when you add those two voltages together, they will always equal the battery voltage. Because the battery voltage is divided between the resistors, a series circuit is often called a voltage divider. Now let's look at another resistor configuration. Here the resistors are connected so that there are two separate paths for current to flow. One path goes from the battery through R1 and back to the battery. The second path goes from the battery through R2 and back to the battery. These resistors are said to be in parallel. Because each resistor is connected directly across the battery, the voltage across each resistor is the same as the battery voltage. The current, however, is divided between the two branches. Some current flows through R1 and the rest flows through R2. The amount of current flowing through each branch depends on the value of its resistance. Lower resistance allows more current to flow, while higher resistance allows less current to flow. And the sum of the current through R1 and the current through R2 equals the total current in the circuit. For that reason, a parallel circuit is often called a current divider. Let's summarize this information. In a circuit with resistors in series, the current is the same throughout the circuit. The voltage is divided across each resistor. This type of circuit is known as a voltage divider. In a circuit with resistors in parallel, the voltage is the same throughout the circuit. The current is divided through each resistor. This type of circuit is known as a current divider. Now let's apply Ohm's law to these two types of circuits and see how we can calculate voltage, current, and equivalent resistance. Here we have a circuit with two resistors in series. Let's make the battery voltage 12 volts. Let's make R1 200 ohms. Let's make R2 400 ohms. With this information, let's find the total resistance in the circuit, the current in the circuit, and the voltage across each resistor. In a circuit with series resistors, the total resistance is R1 plus R2, or 200 ohms plus 400 ohms. The total resistance in this circuit is 600 ohms. We can find the current in this circuit using Ohm's law. V equals I times R, where R is the total resistance in the circuit. Rearranging the formula for Ohm's law, we get I equals V divided by the total resistance. I equals 12 volts divided by 600 ohms. I equals 0.02 amps or 20 milliamps. Next, let's find the voltage across each of the resistors. We know that in a series circuit, the current is constant through both resistors. Since we know the voltage in the circuit and the current in the circuit, we can use Ohm's law to calculate the voltage across each resistor. Let's start with R1, V equals I times R. So to calculate the voltage across R1, we multiply the current times the resistance of R1. The voltage across R1 equals 0.02 amps times 200 ohms. The voltage across R1 is 4 volts. Let's do the same to find the voltage across R2. V equals I times R. So to calculate the voltage across R2, we multiply the current times the resistance of R2. The voltage across R2 equals 0.02 amps times 400 ohms. The voltage across R2 is 8 volts. In this circuit, the battery voltage is 12 volts. If we take the voltage across R1 and add the voltage across R2, the sum is 12 volts, the same as the battery voltage. Again, resistors in series are voltage dividers. The current in the circuit is constant through both resistors. Now that we have explored resistors in series, let's use Ohm's law to calculate voltage, current, and resistance in a circuit with resistors in parallel. Here we have a circuit with two resistors in parallel. Let's make the battery voltage 12 volts. Let's make R1 300 ohms. Let's make R2 600 ohms. With this information, let's find the total resistance in the circuit, the total current in the circuit, and the current across each resistor. Let's work with what we know about a circuit with resistors in parallel. First, we know that the voltage is constant throughout the circuit. It is 12 volts. Next, in order to find the total current in the circuit, we have to find out the total resistance RT. Once we know the total current, we can calculate the current flowing through each resistor. The formula for the total resistance of resistors in parallel is 1 divided by total resistance is equal to 1 divided by R1 plus 1 divided by R2. So 1 divided by RT equals 1 divided by 300 plus 1 divided by 600. We can make a common denominator of 600, so this becomes 1 divided by RT equals 2 divided by 600 plus 1 divided by 600. Thus 1 divided by RT equals 3 divided by 600, or 1 divided by 200. If we invert both sides of the equation, RT equals 200 ohms. The total resistance in the circuit is 200 ohms. Using Ohm's law, we can now calculate the total current in the circuit. V equals I times R. We can rearrange the equation to I equals V divided by R. So the total current equals 12 volts divided by the total resistance, 200 ohms. Therefore, the total current in the circuit equals 0.06 amps or 60 milliamps. Finally, let's use Ohm's law to calculate the current through each of the resistors. V equals I times R. Rearranging the equation, we get I equals V divided by R. Let's calculate the current through R1. The current through R1 is 12 volts divided by the resistance of R1, 300 ohms. The current through R1 is 0.04 amps or 40 milliamps. Now let's calculate the current through R2. The current through R2 is 12 volts divided by the resistance of R2, 600 ohms. The current through R2 is 0.02 amps or 20 milliamps. As you can see, the sum of the current through R1 plus the current through R2 equals 0.06 amps, which is the total current of the circuit. Again, resistors in parallel act as a current divider. Let's look at one last circuit. In this circuit, we have 3 resistors arranged in both series and parallel. How do we calculate the total current in this circuit? Let's set some values to this circuit. V equals 12 volts. R1 equals 100 ohms. R2 equals 200 ohms. R3 equals 200 ohms. In order to calculate the total current in the circuit, we must simplify the circuit. The first thing that we can do is calculate the equivalent resistance in the parallel resistors. We will call this equivalent resistance Rp. So let's get to it. The equivalent resistance of the two parallel resistors are 1 divided by Rp equals 1 divided by R2 plus 1 divided by R3. 1 divided by Rp equals 1 divided by 200 plus 1 divided by 200. 1 divided by Rp equals 2 divided by 200, or 1 divided by 100. Therefore, Rp equals 100 ohms. So let's replace the parallel resistors by Rp, and you see something magic happen. With the parallel resistors replaced by their equivalent resistance, Rp, the circuit becomes much simpler to analyze. Instead of a circuit containing both series and parallel resistors, we now have 2 resistors connected in series, R1 and Rp. Now let's calculate the total resistance of the circuit. Since these 2 resistors are in series, we simply add their resistances together. RT equals R1 plus Rp. RT equals 100 ohms plus 100 ohms. RT equals 200 ohms. Therefore, the total resistance of the circuit is 200 ohms. We're finally in a position to solve for the total current in this circuit. We know that V equals 12 volts. We know that RT equals 200 ohms. We use Ohm's law to solve for the total current in the circuit. V equals I times R. Rearranging the equation, we get IT equals V divided by RT. IT equals 12 volts divided by 200 ohms. IT equals 0.06 amps or 60 milliamps. The total current in the circuit is 0.06 amps. Now it's your turn. Let's return to the original series parallel circuit. After our calculations, we have the following information. V equals 12 volts. The total current equals 60 milliamps. The total resistance equals 200 ohms. See if you can figure out the following. The voltage across the series resistor, R1. The voltage across the parallel resistors, R2 and R3. The current flowing through R2. And finally, the current flowing through R3. I will put the answers in the comment section. Let me know how you did. In this lesson, we expanded our understanding of Ohm's law by solving for voltage, current, and resistance in a variety of circuits. We then applied those same principles to analyze resistors connected in series, in parallel, and in a simple combination circuit. Hopefully, you can now see that even more complex circuits can be broken down into smaller, simpler parts and solved one step at a time. As one final exercise, I'd encourage you to return to the original combination circuit and calculate the remaining voltages and currents on your own. I'll post the answers in the comments below so you can check your work. In our next lesson, we'll shift our focus from resistors to the battery itself. We'll discuss electron flow versus conventional current flow, explain why every electrical circuit requires both a source and a return path for current to flow, and begin relating these concepts to electrical stimulation in neurodiagnostic testing. If you found this lesson helpful, please consider subscribing to the channel, giving the video a thumbs up, and sharing it with friends or colleagues who may also benefit from the series. As always, if you have any questions or comments, please leave them below. I read every comment and will do my best to answer them. Thanks for watching, and I'll see you in the next lesson.